Everyone, welcome back to our last talk of the second day. As our final speaker, we have Anna Romanov from the University of Sydney, who is going to tell us about highest weight structures on Whittaker categories. Thank you, Anna.
Great. Thanks, Nicole. And thanks for the organizers for inviting me. It's nice to be here virtually from Australia. And also my title of my talk is different from the one that I sent in several months ago because the way that I view this project changed a little bit in those months. And so while I was preparing this talk, I was looking at the title of my talk and I was looking at the title of the session and all these things that are on this list and realizing that I really only fit into like a very small subset of these words. So this is our session on categorification, higher representation theory, and homological knot invariance. So I don't really study homological knot invariance. Sometimes I do categorification, but this project is not about categorification. So really it fits into these two words. So it's not higher representation theory, it's just representation theory. But hopefully there are enough representation theorists in the audience, or at least representation theory tangential people, that you might still be interested in what I have to say. So yeah, this is joint work with Adam Brown, who is at IST Austria. And we just put this paper on the archives like a few weeks ago. So if you are very curious about what we're saying, you can go read about it. Okay. So at least the least I figured I could do, since this is a session on categorification, is to start by giving you a category. So here's a category. It's a category whose objects are representations of a semi-simple Lie algebra over C. And the conditions we're going to put on these objects is we want them to be representations which are finitely generated, locally finite for the action of the nilpotent part. So I'm fixing some triangular decomposition of my Lie algebra, and I'm asking that my modules are UN finite. So if I take some vector in the representation and I just look at the orbit under UN, I want that to be finite dimensional, even though the representation itself is probably going to be infinite dimensional. And then I impose one more finiteness condition. I ask that my representations are locally finite for the action of the center of the universal enveloping algebra as well. So this category is sometimes called the Milicic-Zorgel category of Whittaker modules because it was introduced by Milicic and Zorgel in the 90s. And so it's just some category. I mean, I could change these three conditions and cut out some other category of representations of a Lie algebra. So the natural question to ask about it is why do I care about this one? So why am I interested in this category? And I'll tell you a little bit historically why this category came up. So it comes up because it's a natural place where Whittaker modules live. So what is a Whittaker module? A Whittaker module is a certain type of representation of G that's cyclically generated by something called a Whittaker vector. And a Whittaker vector is just any vector in a representation that has the property that n, this nilpotent radical, acts by a character. And so if we have some representation that's cyclically generated by a vector that has this property, then this representation is called a Whittaker module. And I claim that you've definitely seen these before, even if you don't think you have, because probably you've seen a Verma module before. And under this definition, a Verma module is an example of a Whittaker module, because a Verma module is generated by a single highest weight vector. But what makes it a highest weight vector? It's annihilated by n. And so n acts by the zero character. And so a Verma module is an example of one of these Whittaker modules, but the Whittaker modules are more general. So I'm no longer asking that my generating vector just be annihilated by n. Instead, n just has to act by some sort of character. Okay, so that's some type of representation. But these were first studied in the 1970s by Costant. And Costant started studying them not because he was interested in representations of Lie algebras per se, but he was actually interested in representations of semi-simple Lie groups. And he was interested in sort of a specific question about representations of semi-simple Lie groups. He wanted to know when a given semi-simple Lie group admitted what was called a Whittaker model. And this was a certain realization of the representation. So in terms of a certain type of function. So in certain representations, you can realize them as functions. So the vectors in the representation are functions. And the Whittaker models are where the functions are certain solutions to a differential equation called the Whittaker equation. And so this is kind of a useful property. If you know that a representation has a specific form, you can like really deal with it explicitly because you know what the vector space looks like. And he wanted to know when this happened. And what he realized was asking this question was the same as asking when a representation had a Whittaker vector for the corresponding Lie algebra from the semi-simple Lie group. And so this led him to this notion of a Whittaker module. And he actually classified them in a specific case in this original paper. And he classified them in the case where the character was non-degenerate, which is sort of the opposite of the zero character example I gave earlier. So one of these characters being non-degenerate just means that it doesn't vanish on all simple root spaces. So n here, remember we're talking about characters of n, we could take n and decompose it into a direct sum of root spaces corresponding to all positive roots. Because it's a Lie algebra morphism, it's going to vanish on all of the root spaces that are not corresponding to simple roots. But if we have some simple root space in here, either our character can vanish or not vanish. And if it doesn't vanish on any of the root spaces, we say it's non-degenerate. If it vanishes on all of them, we say it's zero. And so Costin studied these non-degenerate guys in his original paper. But in doing this, he introduced the definition of Whittaker modules in general, and it's natural to ask about what they look like for partially degenerate characters or the zero character. And this is where this category comes in. So many years later, actually, I should have written a date here, but this was in the 90s, Milicic and Zorgel introduced this category that I've written as sort of a place to house all Whittaker modules. And this is because the simple objects in this category are exactly the irreducible Whittaker modules. So this is some category that's kind of built around irreducible Whittaker modules, but some of its other objects are not necessarily Whittaker modules. Cool. So this is a category I like. I've spent a lot of my time thinking about it. And one of the reasons I like it is because it has a lot of nice properties. So I'll tell you some of its properties now in an attempt to convince you that you should like it as well. The first nice property is that it has a block decomposition. So if we take any representation in this category, we can write as a direct sum of representations in these subcategories. And these subcategories are exactly the modules that have some generalized infinitesimal character. So the center of the universal enveloping algebra. So this is like a decomposition into generalized eigenspaces for the center of the universal enveloping algebra, and also generalized eigenspaces for this, for all the possible, or for the action of this nilpotent radical. So each of these categories is sort of quite nice. Like one of these smaller categories, these guys, we know exactly how, well, roughly how the center of the universal enveloping algebra acts, and we know roughly how eta acts. And so these are sort of smaller, more reasonable categories, and anything in our category can be decomposed as a sum of modules in some collection of these things. So that's kind of nice. Another nice quality of this category is that it contains category O as a full subcategory. And this lives inside of the blocks where eta is equal to 0. And this is kind of what we saw earlier when I said that Verma modules were Whittaker modules corresponding to the 0 character. All of category O actually lives inside of here. And in some sense, we can think about n as a natural generalization of category O. If we slightly changed the conditions defining it, we would exactly get the definition of category O. Another nice quality of this category is that its objects have finite length. So every module in here has a composition series, a finite composition series. And it also has a very nice classification of irreducibles. So this is due to McDowell. This classification showed up before the definition of the category showed up, because McDowell was actually just classifying irreducible Whittaker modules, but all of the modules that show up in this classification are in this category as well. So it classifies the simple objects in the category. And this classification feels very familiar if you're used to thinking about category O. The way it goes is that we construct some sort of standard module, and the standard modules here have 2 parameters, one parameter corresponding to something in the dual of the Cartan, and then the other parameter corresponding to the character. And these things are constructed through some sort of parabolic induction procedure, which I won't write down precisely, but it's relatively straightforward. And then part of the point of them is that when eta is 0, this construction exactly gives us a Verma module. So we can construct standard modules given these 2 inputs. And then these standard modules give us a classification of simple objects in our category. So all simple Whittaker modules appear uniquely as irreducible quotients of one of these standard guys. Okay, so now we have some category whose objects are finite length, so they have finite composition series. We have a collection of standard objects, and we have a collection of simple objects. So the natural question to ask next is about composition multiplicities. So how many times does a given simple object show up in the composition series of a given standard object? And this is answered in a nice way by Kazhdan-Lusztig polynomials. So the answer to this question is that we can construct an anti-spherical parabolic Kazhdan-Lusztig polynomial that exactly describes the multiplicity of a given simple in a given standard. And the way that this can be seen, well, there are a few ways that we can see this. So the first way that this was proven was by Milicic and Zorgel in their original paper in 97, where they defined this category. And this only worked for certain standard modules, for certain choices of the perimeter lambda. And they built an equivalence of categories between certain blocks of this Whittaker category and categories of Harish-Chandra bimodules, which they were then able to compare to singular blocks of category O. And then they were able to extract this result based on known results about composition multiplicities in category O. So that was where this was first done, but it was only done for certain lambdas. And then immediately afterwards, Backelin showed this in general using these Whittaker functors, which were functors he constructed which went directly from category O into this category of Whittaker modules. And again, this let us conclude that the composition multiplicities are given by parabolic Kazhdan-Lusztig polynomials. And then this can also be shown directly by using geometric techniques. And this is what I did in my thesis. So you can use Valence and Bernstein localization to relate these blocks of the Whittaker category to certain D modules in the flag variety. And then you can construct an algorithm for computing composition multiplicities in the D module land. And then this thing tells you that they're given by parabolic Kazhdan-Lusztig polynomials in a similar way to the original proof of the Kazhdan-Lusztig conjectures by Valence and Bernstein. Okay, so here's a bunch of properties from some category I like. And what you might be thinking right now, if you've learned a bit about category O, is that N looks to be exactly like category O. So it's all the things I've told you so far are some of our favorite properties of category O: block decompositions, character theory being given by Kazhdan-Lusztig polynomials, etc. But in some ways, N is not the same as category O. So there are some ways where this category gets a little bit strange. And these are actually the topic of this talk today. So this is what I want to talk about, the ways in which N is strange. And the first one is that the modules in N are not necessarily weight modules. So one great property of category O is that every module decomposes into a direct sum of finite dimensional weight spaces. And these finite dimensional weight spaces are really useful in essentially everything we do with category O. And this doesn't happen in category N. So the modules are not semi-simple for the action of H. And, oh, sorry, that's not what I wanted to do. And so in particular, what this means is that we can't extend the notion of duality we have in category O to category N, because here's a brief reminder of how duality works in category O. In category O, we have a beautiful duality, which we can define using weight spaces. So if we have some module in category O, it decomposes into a direct sum of finite dimensional weight spaces. Then we can define the dual to be what we get if we just take each of these finite dimensional weight spaces and take its full linear dual. So just C Homs from the weight space to C, and then glue all those dual weight spaces back together and form a module again. And then this thing is another module in category O if we do the correct twisting in our action. And this builds for us a dual module in our same category. So we have some nice procedure where we can define duality quite explicitly, but the duality depends in an essential way on having finite dimensional weight spaces, which we don't have in category N. And so there's not a natural way that we can extend this. And a consequence of this is that it's not obvious how we can define co-standard objects in our category. So in category N, we have these standard objects, which look a lot like Verma modules, and we have simple objects, which look a lot like irreducible highest weight modules. But we can't just take duality and apply it to standard objects to get some co-standard objects in our category. And so it's not clear what or if there should even be a definition of co-standard objects in category N. So that's one way, that's the first way which N is a little bit strange. It loses the duality. And another way that it's strange is that the modules, the standard modules, admit many contravariant forms. So I'll spend a slide talking about this because I think, so I'm not sure how common of a notion this is, but why is this weird? What is a contravariant form and why is this a strange property? So here's a definition. What a contravariant form is it's a bilinear form on the underlying vector space of some representation that is symmetric and behaves nicely with respect to the action of the Lie algebra. So the definition is here. If we act on the left-hand side of something within this pairing, this is the same thing as acting on the right-hand side by the transpose. And so this kind of fits into the philosophy. If you think about the point of representation theory being to utilize the tools of linear algebra to study group theory, which is how I tend to think about it, then bilinear forms of different flavors are a tool we have in linear algebra. And so these are a useful thing we can use to study the symmetries of the group that we care about. And that's exactly what the purpose of these contravariant forms are. So they were first introduced to study, well, they can be used to study Verma modules or other types of representations. But when they first showed up there, it's pretty easy to show that either a Verma module or an irreducible finite dimensional module admits a unique one of these up to scaling. And so the words for this, at least on the Verma module, are the Shapovalov form. And that's because both Verma modules and irreducible finite dimensional modules are generated by a single highest weight vector. And so we can define the form on how it pairs the highest weight vector with itself. And then this contravariance condition here is pretty strict. And so once we know how the form pairs or how the form acts on the highest weight vector, then this tells us how it acts on any other vector in the module, because the module is cyclically generated by the highest weight vector. And the purpose of these forms, or one of the reasons why they were introduced, is because they can be used to define the Janssen filtration of a Verma module. So we have a unique contravariant form on a Verma module, and this can be used to define a filtration in terms of order of vanishing of this form. And this filtration is very useful. This is a filtration of a Verma module that tells us really subtle information about its submodule structure. In particular, this filtration, its filtration layers are semi-simple, and their multiplicities, the multiplicities of irreducibles, are given by coefficients of Cauchy-Lustig polynomials. And so this Janssen filtration tells us sort of more intricate information than the composition series. And in particular, it tells us sort of what the coefficients of Cauchy-Lustig polynomials mean representation theoretically. And this is all built using the machinery of this contravariant form. And this is actually, this is what was Adam and my original motivation for doing this whole project, is that we knew the composition series questions in the Whittaker category. And so we wanted to define Janssen filtrations for Whittaker modules. So we started doing this, but we got stuck immediately in the first step because we tried to write down the contravariant forms. And what we realized, let's go back. What we realized was this theorem, which is that there are too many of them. So if we look at contravariant forms on a standard Whittaker module instead of a Verma module, it has a lot of them. So they're no longer uniquely determined by what they do on the generating vector. Instead, we have a whole vector space worth of them. And that vector space's dimension is given by some subgroup of the Weil group. And this subgroup is exactly the one that's generated by the simple roots where eta doesn't vanish. Okay, so contravariant forms sort of show up in this classical world of category O type representation theory, and they show up in two main ways. One way is to define this Janssen filtration, and another way is that they give us a canonical homomorphism between a Verma module and its dual. Because the way we define a dual Verma module, it's carved out of the full linear dual of the Verma module. So if we have this contravariant form, this gives us a map from m lambda to m lambda dual by just taking some vector and then taking the form or the linear functional we get by pairing against that one vector. And it turns out that this thing lives in the dual Verma module. So this is our canonical homomorphism between a Verma and its dual. And if you're used to thinking geometrically, this is exactly the canonical homomorphism that corresponds on the geometric side to the map from shriek push forward to star push forward. Okay, so this strangeness on contravariant forms is a second way in which this Whittaker category behaves a little bit strangely. Also, maybe I should have said this at the beginning, but everyone, yeah, maybe. Are there any questions? People are very welcome to ask questions if they have them. Or I'll just keep chugging along. Okay, thumbs up from, oh yeah, question.
These modules are not even UH finite.
Yeah, exactly. They're not even UH finite.
And the next question is, oh, I've forgotten that already. Never mind, I'll get back.
Okay, thanks. Cool, so, well, I asked you for questions, but also now I'm going to give you a bunch of questions. So I claimed that all those things I said just led us to some natural questions about this category. So the first one is that I just told you that in category O, one of the roles that contravariant forms play is they capture the relationship between standard and co-standard objects. So we have a bunch of contravariant forms in category N, but there's too many of them. So what are they measuring? What do contravariant forms capture in category N? Another question is that category O is the archetypal example of a highest weight category. The definition of a highest weight category was sort of built off of the structure that's present in category O. And in category N, we have a lot of that structure. So can we give N the structure of a highest weight category? But what does it mean to be a highest weight category? Well, we have some initial data, and then we have to show that it satisfies some conditions. And for something to be a highest weight category, it needs to have some specified set of standard objects, simple objects, and co-standard objects. And so before we can really talk about a highest weight structure on N, we have to have some notion of co-standard objects. And how we get those in category O is we take the standard objects and apply duality. But without duality, how can we define co-standard objects in N?
Question, Emma.
Oh, yeah.
So is there anything wrong with just saying you have this, size of this W sub eta many co-standards from all of these different forms? Like, why not just have like a zoo of co-standards?
This is exactly what I'm going to do. I love it when people ask questions like this.
Okay.
Yes, that's going to be, so we'll see in a few slides from now that this is what you can do. Yeah, you can build multiple co-standards and then show they're all isomorphic.
Cool.
Awesome. So one interesting thing about this last question is that it seems to completely disappear if we think geometrically. So geometrically, there's a D-module version of this category that we get by valence and Bernstein localization. So a block of this Whittaker category is equivalent to a certain category of twisted N equivariant D-modules on the flag variety. And in this D-module category, there is a notion of standard and co-standard object because we have these two different types of push forward, star push forward and shriek push forward. And standard objects are formed by taking the shriek push forward of the structure sheaf on some Bruhat cell. And co-standard objects are formed by taking the star push forward of some structure sheaf. And so this problem with duality doesn't exist geometrically. We have a duality in terms of holonomic duality. So one answer to the first question is, or to the last question, is we could define co-standard objects to just be to say, okay, take a co-standard sheaf. We have a functor from D modules to the Whittaker module. So we just take the global sections of the co-standard D module, and that should be our co-standard object in N. And that's fine. That gives us a definition of co-standard objects, but it's somewhat unsatisfying because it's really unclear by just taking a D module and taking its global sections, what algebraic property is cutting out this representation or this module, because holonomic duality on the D module side doesn't really behave well with respect to any algebraic dualities. And so it's not known if we just take in general in the category of holonomic D modules, if we take duality, what this looks like algebraically at all. So this definition is, in some sense, okay, but in some sense, it's not really a great one because if we like to think, like from my perspective, I care about the representations more than the D modules. And so I'm actually interested in like the structure of the representations. And so I would want to know what it means to be a co-standard object algebraically. Okay, so here are some natural questions. And then the point of this talk is that most of those questions that I just listed, we now have an answer to. And that's what we did in this most recent paper. So the way that this all comes is it actually kind of takes the idea that Monica just proposed, is that we're going to replace contravariant forms with something slightly different called a contravariant pairing. And this is going to allow us to define a bunch of co-standard objects. And so here's how it works. A contravariant pairing is almost the same thing as a contravariant form, except a contravariant form was a pairing between a standard Whittaker module and itself. So it was a bilinear form on one vector space. And a contravariant pairing is now going to be a pairing between two different vector spaces. So it's going to be a pairing between a standard Whittaker module and a Verma module. And then it's going to satisfy exactly the same condition. So it's going to be some function that takes in a vector in each of these modules, and it satisfies this contravariance condition again with respect to the action on either the standard Whittaker module or the Verma module. And then once we have these, we can prove a uniqueness theorem. So the first thing is that there only exists one of these contravariant pairings between a given standard module and a given Verma module exactly if the highest weight of the Verma module is in the W eta orbit of the highest weight of the standard Whittaker module. And if one of these things exists, then it's unique up to scaling. And so this theorem here is capturing exactly the same information as our other theorem. We still sort of have W eta's worth of contravariant pairings in the same way we had W eta's worth of contravariant forms, but now we kind of spread them out. So instead of all being contravariant forms on the same module, we've kind of moved them so each one pairs with a different Verma module. And this spreading out procedure is exactly what we needed to be able to define our co-standard objects. And so here's how we can define co-standard objects using this machinery. So first of all, just a quick definition. If we have some G module X, we can take the collection of eta twisted UN finite vectors. And these are just the vectors in our module that are generalized eigenvectors for the character eta. And then the definition of co-standard objects goes like this. So if we choose some W in W eta, and then we build some corresponding, or then we can take the parameters lambda and eta. These are the parameters that go into constructing a standard module. We define a W co-standard Whittaker module to be what we get if we take the full linear dual of some Verma module, and then take these twisted UN finite vectors within this full linear dual. And this is some procedure that constructs for us a module from lambda and eta. And the point of this definition is that with this definition, our unique contravariant pairing exactly gives us a G-morphism between a standard object and a co-standard object because of the way that this is defined. So if we kind of stare at this for a second, the way that we've defined this dual is as a subspace of the linear dual of a Verma module. So if we fix some vector in our standard Whittaker module and then just take some contravariant pairing and pair against that fixed vector, this is something that's going to take in elements of a Verma module. And so this thing here is going to be some subset of the dual of a Verma module. And it turns out that we can show that it lands exactly in this subset of the dual that we've carved out. So the thing about this definition is it comes automatically with a canonical morphism between a standard object and a co-standard object. Any questions?
I have a question. Can you remind me the relationship between this Verma module and this kind of the standard guy you start with, that this guy is co-standard to?
Well, there isn't really one. I mean, they're both just sort of separate. So the parameter, what I haven't done is I haven't actually told you how the standard objects are defined, but they're defined by taking so eta picks out some sort of Levy subgroup, and then we kind of can build a Whittaker module, a non-degenerate Whittaker module for the smaller Levy subgroup, and then do an induction procedure there. But yeah, there's not really more of a relationship between, I guess the fact that they have the same lambda parameter just means, it means that if you took the infinitesimal character of the Verma module, no, actually the opposite. If you took the infinitesimal character of this Levy thing and restricted it to the infinitesimal character, to the center of the entire universal enveloping algebra, it would give you the infinitesimal character of the Verma. So they sort of like live in the same infinitesimal character block is basically all.
Yeah, I guess I was kind of thinking like, what would make you think to look for it here? Like what would make you think to go to this Verma and do this construction? I mean, it's great, but I was just trying to if I were to recreate it, why would I try this? Like why would it occur to me to try to go in the Verma?
Yeah, well, actually, I can kind of tell you. I don't know if this is a bit of a tangent, but
we can also save it for the end of the talk in case you want to.
Yeah, I think I have time. Actually, it's an interesting thing. So the reason we came to this is because, so if you think about what duality looks like in category O, or for any module, you always have a map. So any choice of contravariant form gives you a map from a module to its full linear dual. So just Homs from the module to C. And then what happens in category O is that if you look in the full linear dual, you can pick out a unique highest weight vector, and that vector carves out for you the dual Verma module within the full linear dual. And if you do this for a Whittaker module, if you take the contravariant form, it gives you a map into the full linear dual of the Whittaker module. And that's just a huge thing because Whittaker modules are already like more infinite dimensional than Verma modules. And so then if you take their dual, it just becomes giant. And this dual has lots of Whittaker vectors. So it no longer has a unique like a unique Whittaker vector like it does in the Verma case. And so it's not clear how to pick out like which Whittaker vector you should use to carve out your dual in your category. And so you actually have W eta's worth of choices. And so you kind of could choose any of that's like where we see the different contravariant forms. So you have many different choices for which one to carve out. And so for a long time, we were trying to construct the definition of a costandard by taking some subset of the full linear dual, but it was too big. And so then what we realized is that we could actually just take a subset of the full linear dual of a different module, the Verma module, because that was kind of smaller. And so that gave us a more reasonable definition.
And so does that mean there's only one Whittaker vector inside the dual of a Verma?
Yeah, but the parameters have to line up right. So there is not in any Verma, but in this case where the highest weight of the Verma is in the W eta orbit of the Whittaker vector. Yeah.
Cool. Thank you.
Cool. So I think I'm almost done now. But as we'd hoped, the nice thing about this definition of costandard objects is they satisfy all the things that we would want costandard objects to satisfy. So this is kind of the main result of this paper. The first is that by the construction, I've just constructed for you a whole bunch of different costandard objects, one for every element of this file group. But it turns out that if we choose two different elements, they're isomorphic as modules. And so it seems like we built a bunch, but they're all isomorphic. And so we can just choose W to be the identity if we'd like. And then we can drop it from our notation entirely and say that we have up to isomorphism, a unique costandard object corresponding to these parameters. And then we can show that our costandard object has the correct irreducible as a unique submodule, which is something we'd want it to have. And then we can show that it has the same class in the growth indie group as the standard object, which is another property we'd hope costandards would have. And then kind of by construction, we have this canonical morphism between our standard objects and our costandard objects. So it satisfies this property. And then the last one, which is one that I like especially, is that we can show that this thing is isomorphic to the global sections of the costandard D module. And so this fits with what we might call the definition from earlier. Like we could just take these global sections. And so what we've realized is that this algebraic characterization exactly tells us what how you should think algebraically about the global sections of the costandard D module. So this gives us, an algebraic characterization of at least sort of this one piece of holonomic duality. And then, so this answers some of the questions that I had on that slide earlier. And it also answers kind of the middle question, which is now we have a category that has standard, simple, and costandard objects. And so we can show that with respect to these costandard objects, blocks of category M do have the structure of highest weight categories. And so again, something that's slightly subtle here is that all of category N doesn't necessarily, but if I take these blocks where I have a fixed infinitesimal character, so not a generalized infinitesimal character, a legitimate infinitesimal character, and then a generalized N character, these things have the structure of highest weight categories. And then this is really nice because the part of the highest weight category machinery is that it gives you a bunch of extra structure. And so once we know these are highest weight categories, we can build a BGG reciprocity theorem in this setting. Because by the fact that they're highest weight categories, we automatically know that they have enough projective and injective objects. And we know that projective or injective objects have filtrations by either standards or costandards. So if we take the projective cover of some simple, then we can ask about multiplicities so now we can talk about multiplicities in the standard filtration of this projective. And we can state sort of an exact analog GG reciprocity that works in this Whittaker category, which is that the multiplicity of some standard in some projective is equal to the composition series multiplicity of the corresponding simple in the standard. So that's kind of a nice application of this. Any questions on the spin? I have until 9, right?
Which is the order in the the order
In
between the
Reciprocity? You mean here? Oh, sorry, the post-it order. Great question. I even had it, let's see, there. So the order in the highest weight category is a Bruhat order on this quotient. So there are bits of the structure of the Whittaker category that I've kind of glossed over here, but within one of these blocks, within one of these blocks, the standard modules here are actually parameterized by longest coset representatives in this quotient. So there are different choices of lambda that will result in the same in an isomorphic standard module. And these two things are isomorphic exactly if the lambdas are in the W eta orbit of each other. And so there are this quotients many different standard objects and different simple objects and different co-standard objects within one block of the category. And so then the poset is just the Bruhat order on longest coset representatives here. Yeah, good question. Any other questions? Oh, I have something in the chat. Okay. Oh, I'm over by a minute. I thought, okay, well, it's okay. This is my last slide. So, so I'll just leave with some other questions about this category. So last questions about the category is that now maybe we have some hope of answering our original question, which was we wanted to find Janssen filtrations on standard modules. And now contravariant forms didn't work. There were too many of them, but maybe we can use contravariant pairings. And so this is what we're going to try to figure out next, is if we can define some notion of a Janssen filtration using contravariant pairings instead. And then we still have this question that we're not really sure what contravariant forms measure. So I have some interesting ideas as to what they seem to be doing on the D module side. Like they seem to sort of correspond to extra equivalences of categories that you get from intertwining functors on D modules, which is kind of neat. But they are sort of a strange feature of this category. They almost seem like the wrong notion for the Whittaker category. And then the last thing is that now that we have a highest weight structure, we can talk about tilting objects, and we can ask about characters of indecomposable tilting modules, and that's a question we can ask, and we'll ask at some point in time. We're not quite sure what the answer is yet. And that's all I have. Thanks.
Thank you, Anna. Let's thank our speaker. That's a great rendition of your song. Does anyone have any questions in addition to the ones that were already asked? Yeah, Ben seems to have one.
I have a couple questions. That was excellent talk. Does N have translation functors?
Yeah, at least geometrically, it definitely does. I've never thought about them algebraically, but I think Adam has. Yeah, Adam used algebra. Yeah, it does, and Adam used those in his thesis. And geometrically, the translation functors work exactly the same.
Okay, cool. My second question, like I don't know why I came to this conclusion, but when you said that there were, so such and such a dimensional space of different contravariant forms. So is there some kind of deformed category N, like there's deformed category O? Do you know deformed?
Oh, this is so funny. I don't know the answer, but this is. Oh wait, you mean for the Janssen filtration? Actually, wait, what kind of deformation?
I actually mean just it's just a general question. Like, can you throw in a polynomial ring and have it act via the isomorphism, or because
yeah, so I don't know the answer, but this is the same question that Daniel Tubenhauer asked me when I gave this talk about like 2 weeks ago in Bond's over seminar. And so, and Daniel has just arrived in Australia. And so I'm hoping that we will talk about this together sometime soon, once he ever gets out of hotel quarantine.
It's funny because
the center. Oh, sorry, go ahead.
You separated out all these different copies with different elements of the wild group, and this is exactly the sort of thing that deformed category O kind of does for free for you. Like it separates out different weights of the same central character, basically. Because
what's the center of the category, right? You could ask that and then try to deform over that.
Yeah, that's right.
Oh, yeah, I've never thought about that. Yeah, I'm not so familiar with deformed category O really, so I would have to learn about that first.
Somewhere, I think Tina Kanstrup has notes from a class by Roman Bezirkovnikov. I've never tried to read those notes, but I was in the class when I was listening.
Yeah, I'll look into that. That would definitely be interesting.
All right, thanks.
Any other questions for Anna?
I guess, is there some kind of version of integrability? Like, are there some objects in N that are,
Oh, that are integrable?
or what about just unitary, like positive definite?
So not,
Hermitian version of the form.
oh.
Because I mean,
So
for usual category O, I think integrable and unitary are the same, right? Or like a Kac-Moody algebra.
Yeah. Yeah, so I mean, by integrable, aren't only the finite dimensional representations integrable?
I mean,
Like if by
right,
integrable you mean,
for finite dimensional complex semi-simple algebras, that's true, but for Kac-Moody algebras, of course.
oh yeah, so all of this is just done for finite dimensional complex semi-simple algebras. And actually I'm currently like in an ongoing work, I'm trying to figure out what this category looks like for affine Kac-Moody algebras as well. And that's like a lot more interesting because these non-degenerate Whittaker modules get very strange in that case. But I don't think they're going to be integrable still. Like I think that they're sort of this class of, even in that setting, the class of Lie algebras that don't really correspond to representations of groups. But they are very interesting in the affine case. What I've been trying to do is build the D module theory there, and it's strange.
Great. Oh, sorry, go ahead.
Well, I just had a quick question. Great talk, by the way. Was it known that there were projectives in this category before your result?
No, that's one of the consequences. Yeah.
All right, if there are no more immediate questions, let's thank our speaker one last time. Thank you, Anna.